We're now delighted to have as our speaker this evening Massimo Stiavelli. And as I mentioned, his lecture is entitled Cosmic Dawn, the first stars and galaxies. I'd like to say a few things about the lecture and then introduce the speaker. And then we'll hopefully have a very exciting presentation by Dr. Stiavelli. The talk this evening will concentrate about a particular part in the evolution of the universe from the time when hydrogen was, and some of you, most of you may be familiar with the Big Bang theory, which is the basis of the speech this evening, but essentially cover a period from the time where hydrogen, created through the Big Bang, was essentially recombined, and the time where the hydrogen get reionized again further down in time. And the first time, which time-wise, give you an idea of what times we're talking about, the time where hydrogen was essentially fully recombined was about 380,000 years after the Big Bang event, when the terms of the universe came down 3,000 degrees Kelvin, and therefore the ionization stopped. And at that point, the universe became transparent, so consider radiation, which now we detect as microwave background radiation after 13.7 billion years of time. And then the second part is when reionization occurred through a number of processes that the speaker will talk to us about, and that's about 500 million to 1 billion years after the Big Bang. So tonight we'll be talking between 380,000 years and 500 million to 1 billion years. As you know, Earth is about, 4.5 billion years old. Our sun is about 5 or 6 billion years old, so you get an idea of the time scale we're talking about. Now, during that period of time, from 380,000 to 500 million to 1 billion years, we had very light elements composing the universe, essentially hydrogen, helium, some lithium, and some deuterium, and therefore the structure, what occurred is very unique at that time period. So the planets formed, or the stars, and then of course the galaxies consisted of light wave elements, and therefore have less mass than, let's say, what happened later on after the billion years of the life of the universe. So that was a unique period of evolution of our cosmic evolution. So the speaker is going to talk about that period of time, as I already mentioned. Now, Massimo Stiavelli earned his PhD at the Scuola Normale Superiore of Pisa. As I found out during the dinner time, the name sounds very familiar if École Normale Supérieure. It turns out that Napoleon Bonaparte founded the school in the 17th, 18th century, when France occupied Italy for some period of time, when Napoleon was in charge of that whole territory. So he tried to fashion the school in the same way as the École Normale Supérieure was founded also at that same time in France. So Dr. Stiavelli got his PhD there. Then he moved to Rutgers University in New Jersey. And from there he went to the European Southern Observatory in Garching, Germany. Then he went back to his alma mater, I guess. And from there he came to Baltimore to work at the Space Telescope, the Webb, James Webb Telescope project, where he's at the moment employed. He is actually a member of a group of that whole organization, which deals with the things that he'll be talking to us this evening. Dr. Stiavelli has authored numerous papers in refereed journals, technical reports, and he is also the co-author of 3 books. He is the leader of the Hubble Deep Space Field, has served on and chaired numerous NASA committees, and he is an interdisciplinary scientist on the Science Working Group of the James Webb Space Telescope. He is a member of a number of associations and societies such as the American Astronomical Society, AAAS, American Institute of Aeronautics and Astronautics, and the International Astronomical Union. And without further ado, I'd like to invite Professor Dr. Stiavelli to join us at the podium.
I have a somewhat ambitious plan tonight. Instead of just going into the Hubble data and maybe describing what the James Webb Space Telescope will be able to do, I'd like to give a bit of a theoretical framework of why we think that certain observations are meaningful and what we think they might mean. The other thing I'd like to point out right at the beginning is that, when the president was giving us the ages in the history of the universe. One could wonder, why do we care about the beginning, the first 10% of the life of the universe, or the life of the galaxies? And, there are many answers, but let's think about the development of a human being. Let's suppose that the human being lives 100 years. Why do we care about the first 10 years of life? Those are the years of the fastest evolution, the first word, the first steps. The years where the rate of change is the fastest. Turns out that the same applies to the universe and to galaxies. So that's why we care. So I'll be giving a little overview of cosmology, the framework that I will be assuming. What do we know about the formation of the first objects in the universe? The reionization, and when I say reionization, I mean reionization of hydrogen. It has been, due to lack of caution, we didn't know that an expert in the reionization of helium would be in the room, and I saw her earlier, but here by reionization I mean hydrogen, and the energy sources for it, the when and the who. Then I'll describe what has been done with Hubble on the observation of the first stars and galaxies, and I'll say what the James Webb Space Telescope will be able to do. So modern cosmology, I like to start from this picture. This is a picture from the COBE satellite of the universe after the Big Bang, at the redshift of about 1300. I'll give a definition of redshift in a few slides, but it's about the 300 or 380,000 years after the Big Bang. This picture has enhanced contrast. If I showed it with normal contrast, it would look pretty homogeneous. The differences here are of the order of few parts in 10 to the 5. So the universe at this time was very homogeneous and isotropic, but these things of different colors represent variations in density and temperature in different areas, and we'll come back to that. The heroes of my story are pretty simple, humble guys. Hydrogen, protons, electrons, molecular hydrogen. Now, it turns out that molecular hydrogen is the most common molecule that you have in these early times. And the reason it's important, we'll see that, but the thing I wanted to point out is that due to a rather complex series of processes, actually molecular hydrogen can be dissociated by photons that have less energy than those that ionize hydrogen. And so this means that hydrogen cannot shield molecular hydrogen, and this will become very important later on. But this is all we need to know for the moment. So this is a picture of the universe. We are here next to Hubble. The Big Bang is here, everywhere. And this is more or less where we get to Hubble, with Hubble, about 1 billion years to 700 million years after the Big Bang. We know that at this time, most hydrogen in the universe is ionized. How do we know that? Hello? We know because of this. If we look at some very distant objects called quasars, and we take one that is reasonably nearby and one that is a bit further away, these are their spectra, their energy distribution as a function of observing wavelength. This object is roughly a continuum, and there are a few dips. These dips are absorption lines due to neutral hydrogen clouds between us and the quasar. It's only a few of them. And in fact, this big dip is due to neutral hydrogen in the solar system. So this is represented detection of the solar system, in case you had any doubt. If you look at this other quasar, which is much more distant, you see a lot of dips. This is called the Lyman alpha forest in jargon. However, the upper envelope of the curve is pretty much the same as here. This means that there is no diffuse neutral hydrogen in the universe between us and this object. The same is true for objects at higher and higher redshift. So we know that in our neighborhood, redshift 3, 4, 5, there is no diffuse neutral hydrogen in the universe. However, because of the copy picture that we saw earlier, we know that hydrogen was neutral then. So something between here and there must have happened. If you model what happens when the temperature of the universe goes down, you see that as the temperature goes down, the universe is not able to remain ionized. Protons and electrons recombine, and they form neutral hydrogen. If you had a very simple model, this would happen to completion. There would be no protons and electrons left. It would all be neutral. If you do the right non-equilibrium calculation, you see that it's mostly neutral, but a small fraction, say 2 parts in 10,000, remain ionized. And this doesn't seem much, but actually is very important for what we are going to say later. So it's the vast majority becomes neutral, but a very small fraction remains ionized. So somewhere between this moment when the vast majority becomes neutral and this moment when it's mostly ionized, something must reionize all hydrogen in the universe. Now, this is if you think about it for a second, this is a big proposition. You're talking about all hydrogen, and hydrogen is the most common element in the universe, so you are reionizing the whole universe. So let's start thinking about how do the first objects form, because something must have done it. And let's go back to our picture. These things, the blue and red areas, are density perturbations in the universe. Some areas are slightly denser than some other areas, at the level of few parts in 100,000. So it's a very small difference, but it is a significant difference. Over time, the parts that are overdense will collapse because gravity will pull them together. If you do computer simulations of what happens, that's what you see. So this is a good time to talk about redshift. 1 plus z is the ratio of the universe today and that at a given time in the past that you're referring to. So when a redshift 9, 1 plus z is 10, and it means that a redshift 9, the radius of the universe, or the scale length of the universe, was 10 times smaller than it is today. At redshift 99, it was 100 times smaller than it is today. It is also the ratio of the wavelength of light that we observe over the ones that was emitted. So if you have an infrared photon, if you detect an infrared photon today at 1 micron, at 10,000 angstroms, and you know that that photon is coming from redshift 9, you know that it was emitted as an ultraviolet photon with a wavelength of 1,000 angstroms. So if you do a simulation from redshift 18 to redshift 0, as in this example, you start from very small perturbations, and you see that over time these perturbations grow. The things that were a little bit denser become more denser and denser, and the underdense ones becomes things that in jargon we call voids. So perturbations grow over time because of gravity. Why is it that some become denser and some don't? Well, it turns out that, for those with a background in physics, or it's Gauss' theorem. In gravity, you only care about, if you want to study what happens on a sphere, it only matters the mass that is within that sphere. So if you have an overdense area, that area doesn't care about what's outside. It behaves like a universe that is overdense. And an underdense area behaves as a universe that is underdense. So the overdense one will collapse, and the underdense one will expand. And because of the way gravity works, actually this, when you collapse, it happens in a non-symmetric way. So the overdense things become more and more filamentary, and the underdense things become rounder and rounder. That's why they appear as voids in the simulation. So you end up with things like that. And galaxies are along the filaments, and clusters of galaxies are in the center. So we understand why the computer simulations show that behavior. So let's focus now on a perturbation that is overdense and collapses. If it was ideal matter, it would expand a little bit, and then as gravity takes over, it would recollapse, and it would recollapse to a point. But this is for ideal matter. Real matter is not ideal, and real matter doesn't like to be all in a point. We wouldn't like to be all in a point. We would start fighting each other if we were forced to be in a single point. So this fighting each other of matter is a drive to achieve equilibrium and gets to a certain physical size. The equilibrium in our jargon is called the virialization. And what happens once you reach this equilibrium is that the density of the perturbation is 178 times higher than the density of the universe at that time. So when a perturbation collapses and achieves equilibrium, is 178 times the density of the universe at that time. And this 178 is a number made of pi squared 3, pi squared 18th, and so on. So it's a number that can be computed analytically. So that density depends on the redshift, is 1 plus z cubed. And when it virializes, the gas in this perturbation acquires kinetic energy. And it needs to do so because it needs to balance the attraction of gravity. That's why it stops contracting. You have gas that moves around, and that balances gravity. And we know that kinetic energy balances gravity because, for instance, the motion of the Earth around the sun balances the attraction of the sun. And the temperature of a cloud is about 2,500 degrees for a 10 to the 6 solar masses cloud at redshift 30. Now, is that enough to form a star or to form us or a chair? No. It turns out that the density of the sun, which is about the density of water, is 30 orders of magnitude higher than the density of the universe. If you form something at redshift 30, which is 178 times denser than the universe at that time, that is only 5 million times denser than the universe today. So this is only a little bit more than 6 orders of magnitude. So you have 24 orders of magnitude to go. There is something that needs to bridge the gap between that little initial collapse and the density of things like the sun today. And that's a big gap, 24 orders of magnitude. The beauty of astronomy is that if you have a wrong idea, you can realize it because it's not just a factor of 3 off. It's like a factor 10 to the 24 off. So how do you bridge that gap? You bridge that gap by cooling. Now, what does that mean? This cloud that has collapsed has random motions that balance gravity. Random motions have a name in our world. They are called heat or temperature. When kinetic energy is in a random form, you call it temperature. And if something is hot, you can cool it down. So in order to get rid of the random kinetic energy, which is thermal energy that balances gravity, you need to get rid of it, to dissipate it. And if you remove it, the collapse will restart. By the way, please, if you have clarification questions, ask them at any time. Otherwise, this ends up in a disaster. So don't be shy. So to dissipate thermal energy, you need a cooling agent. And, cooling agent in our homes is the air conditioning system. You need an air conditioning system for these clouds. Now, it turns out that hydrogen, which is most of what's around, is not enough. Why? How do atoms cool down? Imagine the basics. You have atoms going around, and occasionally they hit each other. There may be a transfer of energy during the collision. If that transfer of energy can excite an internal energy level of the atom, then that atom can emit a photon, radiate away that energy, and it has subtracted, it has converted kinetic energy into radiation, so it has cooled the cloud. But of course, if the collisions are not strong enough to excite this level, you're out of luck. They just bounce around, exchanging energy with each other, but they will not cool down. So it turns out that the smallest energy level of hydrogen is 3.4 electron volts. That corresponds to a temperature of about 37,000 degrees. So if your gas has a temperature that is well below 37,000 degrees, practically below 10,000 degrees, it cannot cool. Hydrogen alone cannot cool below 10,000 degrees. So below this temperature, you need something else. And that something else is called molecular hydrogen. That's why I talked about it earlier. There are two channels to form molecular hydrogens in the universe. And you need to form it because, of course, during the Big Bang, it was far too hot to have any molecule. So you need to form it. And these two channels use what, this is pretty embarrassing chemistry, if there is any expert in chemistry in the audience, but this is what we deal with at the high redshift. This is what we would call a catalyzer. So this reaction uses an electron as a catalyzer. This uses a proton as a catalyzer. It's a catalyzer because you use one, but it's returned at the end. The same here. So through the catalyzers, you combine two hydrogens and form a molecule of H2. So now you see why it was important that the universe wasn't exactly neutral after recombination, but had that little fraction of ionization, because that little fraction of ionization provides the electrons and protons that enable these reactions to happen. Without that little residual combination, maybe we wouldn't be here today, or we would look very different. My radius and mass would be much larger than they already are. So we rely on these free electrons and protons as catalyzers and form molecular hydrogen. It's not a lot of molecular hydrogen. It's 2 parts in 10 to the 6, and they get formed at about redshift 100 and redshift 50. This is a calculation of the logarithm, sorry, I forgot to add log, of the molecular hydrogen fraction. Doesn't matter the value, but it's not a lot, but we can work with it. Yes?
Couldn't the hot cloud also cool the evaporation, the hottest hydrogen atom, leave it, and remains as cooler and collapses?
It is not significant as an effect. Keep in mind that while this happens and you can have a little bit of evaporation, the rest, there is additional matter that keeps piling on, adding kinetic energy to the process. And that more than compensates the loss by evaporation. So you really need an active component in cooling. But yeah, that's a good point, but it's not enough. So we talked about a cooling function. A cooling function is something that multiplied by the density of hydrogen gives the rate of loss of energy, so the amount of cooling. And this cooling function for hydrogen, as you can see, drops down dramatically at 10 to the 4, at 10,000 Kelvin degrees. Luckily, molecular hydrogen chimes in and can contribute. Just to be clear, molecular hydrogen is a pretty poor coolant. We don't use it in the radiators of our cars. Metals, even in much smaller fractions, are much better coolants. But of course, in the early universe, before any single star has formed, the amount of metals is pretty minimal. I mean, nothing to speak about. I should say that astronomers like me have the bad habit of calling metals anything that is lithium or heavier. So for us, simple minds, the universe is made of hydrogen, helium, and metals. So in our naive view of the universe, carbon, nitrogen are all metals, okay? So, but aside from this little detail, individual metal atoms. And the reason they cool down is the same I was saying initially, that in a collision, you need energy levels to work with. And metals have a lot more electrons and a lot more energy levels to work with. Yeah, they would help too, yeah. So, if you are going to something that is 1,000th the metallicity of the sun, metals are already driving the cooling. So we are focusing on things that are less than 1,000th of the sun. And if you want to talk about the metallicity of this primordial matter coming out of the Big Bang, it's like 100 million times less of the sun. So there are really no metals to work with. So, to summarize, the first stars form from the primordial material, which has essentially zero metallicity, and they are called in our jargon population 3 stars. And they form in an area, in an age of the universe that we call the dark ages. It spans about 7% of the age of the universe. And in this area, you get the first sources of light, these stars, which may or may not be the same thing, the reionization of hydrogen and the reheating of the intergalactic medium, which comes with it. And I cannot answer questions about why the two are connected. So you now have this cloud, you cool it, you get rid of some of its thermal energy, so it can restart to collapse. There is a quantity in physics that is called the Jeans mass, that it depends on temperature and density, that essentially gives you a condition for gravitational instability. If your mass exceeds the Jeans mass, you collapse. Now, initially, the Jeans mass is larger than the total mass in the cloud. So obviously the condition of having more gas mass than Jeans is not satisfied because everything you have is not enough. But as it cools down, the Jeans mass approaches the mass that you have. And from the point that these two curves intersect, you can collapse. This is not so important. What is important is that the collapse happens at about 200,000 solar masses. We call these mini halos. If you have much larger halos, hundreds of millions of solar masses, they can cool without molecular hydrogen because they are hotter. But we'll focus initially on these. So you have this cloud. It's at least 200,000 solar masses. Cools because of molecular hydrogen, slowly shrinks in size as it's cooling, hits the Jeans mass, bang, goes with a collapse, and forms one star. The reason it does so is that these objects are the first objects in the universe to collapse. So the things that typically complicate life, like objects giving torques that generate angular momentum or generate metals and so on, they don't exist. This is the first object in a given volume of the universe to form. And so it's simpler than any other object that will form later. It hasn't been affected by anything else and will affect everything else. So that's why they're called the first stars. And we think that these objects are very massive. They form out of about 100,000 solar masses of gas. The formation process is probably not very efficient. So we think that they have a mass of maybe 300, 500 solar masses. So they are pretty big stars, but they are not, completely unheard of. And And they form very fast before they have a chance to fragment and forming several little stars. Yes?
Would they form at the intersection of those strands, and would they then, in fact, be sort of the seed crystals from which galaxies would eventually develop? Not that they're spawning galaxies, but they're generating the metals that...
Yeah, yes and yes. But the filaments at redshift 30 or 50 are very, very weak. That's why I started my simulation at redshift 18. So, that's where the filaments will start, but yes. So, what happens? Turns out that these stars are not very friendly. Each of them has enough ultraviolet luminosity to destroy the molecular hydrogen in 1,000 of those objects that haven't formed yet. So the first one that forms kills 1,000 of its brothers. It doesn't do it right away because first it has to kill that cosmological molecular hydrogen that have formed. So there is a little bit of shielding, but after that is destroyed, they destroy all their brothers. So what that means is that they would form, they are pretty rare objects. They would form following these curves, but at some point they destroy the molecular hydrogen in the universe, the one that formed soon after the Big Bang, and instead of going up like this, they go up like this. So there is what we call a negative feedback. Forming first stars kills other first stars. You can do, this is just radiative, just because of the radiation. Yes.
But what volume of space do you take in? Because space is full of mass, and take a big enough volume.
Yeah, remember that this is an overdensity. We're concentrating from something that was separated itself from the expansion of the universe and recollapsed. So I'm talking about this cloud, the specific cloud that recollapsed. Surface is a little bit of nebulous, but there isn't a lot of mass there. Ah, okay. So, okay. It doesn't change very much beyond the maybe a factor of 2, but yes, there is a little bit of ambiguity. Yeah, well. So this is a more sophisticated calculation where we take into account also a number of other factors, like if one of your progenitors formed a star and made metals, you're not going to form a primordial star anymore because you have been polluted by those chemical elements. Or if your neighbor formed a star, you're not going to form something because you have been killed. So taking some of these factors into account, this is what happened. The population 3 stars from mini halos with no metals plateau rather early on, a pretty high redshift. You can form generations of low but non-zero metals later on, and these will make galaxies. And you can form even later on stars, maybe, that have no metals but come from these larger halos that don't need molecular hydrogen to cool. And maybe we don't want to think about that, but they could exist. So we now know how to make stars. They are rare because they kill each other. They are very massive, extremely bright. We need to reionize the universe. Are they the guys who do it? Let's look at the energetics. If you fuse 4 protons into a helium nucleus, you release about 7 MeV per proton. The energy to reionize hydrogen is 13.6. So if you were to reprocess in stars 2 parts in a million of all hydrogen in the universe, you would have enough energy to do it. However, this is very unrealistic because it would require that all that energy is released exactly at the minimum energy needed for ionization, no less, no more. Because if it's more, you waste it. If it's less, it doesn't do the job. Using some more realistic models, it turns out that you need probably 30 times higher. So a fraction of 6 parts in 100,000. And if you assume a reasonable yield of metals, a reasonable model for stellar structure, you find that the metallicity of the universe at reionization is about 1,000th of solar. So the energy, when you make energy from a star, you make metals. The two are one and the same, because a star produces energy by fusing lighter things into heavier things. And we call the heavier things metals. So the same process that releases energy from a star makes metals. And if you connect the two, you find that you need about that metallicity at the end in order to reionize all universe. So that alone tells you that it cannot be first stars, because in the process of doing it, they would enrich the universe beyond what a first star does. This is a bit of a technical point, but which I'll skip, but we can go back if... So, who does it? We expect that it's galaxies that do it. We think that active galactic nuclei, that's quasars, this is black holes accreting matter, cannot do it or cannot contribute because they're very energetic. They will reionize helium. Helium, we know, reionizes later, maybe a redshift 3. So it would be odd if helium reionized, recombined, and reionized. And also, we see that the quasars we see, even with some extrapolations, don't contribute enough flux. So it has to be stars or galaxies, and we suspect the stars alone don't do it. This is a simple model of what stars can contribute, and it's only a fraction of what you need. And you need to go to 1 to reionize completely the universe. So the bulk of it must be done by galaxies. So we have just spent a lot of time describing how you form the first stars, and then we concluded, okay, that doesn't have reionization. But it's still interesting because these are the first objects producing significant amount of metals, significant amounts of the material that we are made of. So when does this happen? Looking at a lot of quasar spectra, these are very distant sources, we can see that it happens around redshift 6, billion year to 700 million years after the Big Bang. If you use different indicators, you find slightly different redshifts. So the data are compatible with something like this toy model, where you have a contribution from the population 3 stars and a contribution from more metallic, more familiar type of objects. So it's very likely the reionization started at a very high redshift, maybe higher than 10, and continued down to something like 6.5. Who did it? We saw that stars probably don't do it. We can have simulations, but the simulations are rather pitiful nowadays. Our most powerful computers cannot simulate even a dwarf galaxy. These galaxies that are formed and that you find in papers have only a handful of stars at most. Obviously, we want to do more work on that. There are some indications that, it's pretty clear that the first galaxies that form actually have some metal content around these 1,000 solar or so. It's possible that very isolated objects forming later on may be primordial in metallicity. That would be interesting. But probably most of those that reionize have actually some metal content. So now we know what to look for. How do we find them? A technique that we use is called the Lyman break technique. And it's done using pictures rather than spectra. Now, the saying among astronomers is that a picture is worth 1,000 words and a spectrum is worth 1,000 pictures. Unfortunately, it takes a lot of signal to get a spectrum, which is the distribution of energy as a function of wavelength. And so for very faint objects, we need to take pictures. The idea is that intermediate neutral hydrogen will absorb completely the flux, or almost completely the flux, at short wavelength. So if you have filters, you can see something that is roughly flat here and then it drops down all of a sudden, you know that it's an object at high redshift. And you can model the redshift distribution. To give you an idea of how difficult it is to take spectra, these are some galaxies in the Hubble Ultra Deep Field South. The red dots are the ones that we think are at redshift 6. This dotted line is the line, the signal to the line where you could get a spectrum of the objects with 1,800 hours of integration on the Very Large Telescope. Yeah, it's an 8-meter telescope in Chile. 1,800 hours of good weather and dark sky. So that's in a single point. So that's likely more than 1 year worth of observations. And it barely gets the brightest. So the bulk of the population is beyond what you can do with present technology. That's why we use this Lyman break photometric technique rather than getting spectra. We have tested it where we can, and we think it works. But it's a little cautionary remark. So early looking at these, we discovered that pushing Hubble at its limits would enable us to probably find the objects responsible for reionization. So this plot shows a white area, which is where we should expect in a magnitude density plane, expect the objects responsible for reionization. Things that are here are impossible because it would mean that reionization has produced more metals than we see. Things that are below this line wouldn't help us because it means they wouldn't produce energy enough for reionization. So if you are in this wide area, you produce enough energy to do it. And previous surveys couldn't probe that area, and the ultra-deep field was sensitive to the left of this line and higher than this other line, could. And so, that was essentially the motivation for doing the ultra-deep field, trying to find the objects responsible for the reionization of the universe. This is a picture of the Hubble ultra-deep field. In fact, it's the first picture that I've seen whether you can see with the naked eye on a good projector in a dark room, which is not exactly our situation, a galaxy redshift 6. And I can't find it now, but it's somewhere here. And there are another 50 or 100 of them. Oh, I already changed. Oh, it's getting better and better. I think it's this guy here. So then we went back with a wide field camera 3 and we took infrared pictures and found galaxies at redshift 7 and 8. And we other surveys to find rarer, brighter objects. So all in all, this ended up being a major effort with the Hubble Space Telescope. A number of programs joined forces. It's about a total of 2,000 Hubble orbits. Hubble orbits the Earth every 96 minutes. So including efficiencies, you're talking about 5 million seconds of observing time on a single spot in the sky. In fact, it's 3 spots. 3 spots, one close to the other. They gave us a pretty good view of what's there at this very high redshift. And what we see is that the light, the amount of light that these galaxies emit is decreasing as the redshift increases. Early on in the universe, it actually increases. You get from now it's a quiet time. Early on, as you go back in time, galaxies become more and more active. But from a certain point on, they start becoming less and less active. As you would expect if you're really approaching the time of the first galaxies. And you have these galaxies, you know how much light they emit. How can you estimate what is their contribution on reionization? There are a number of assumptions. The most serious one is this. It's called the escape fraction. So if you have a cloud of gas and you have some bright stars in it, they emit radiation. Some of this radiation will bounce around. Some of it will hit another cloud. Some of it will ionize something that recombines. only a fraction of it escapes to sufficiently large distances to ionize. And that fraction is called F, and it's not very well known. In the nearby universe, measurements tend to give extremely low values. Some measurements and theoretical arguments at high redshift give very large values, close to 1. I'm sure that it will be between 0 and 1, but what it is we don't really know. So if you combine all the observations together, at redshift 6, 7, and 8, you see that with reasonable models, don't forget about the specific parameters, and low metallicity galaxies, with some escape fraction of the order of 14, 15%, the galaxies we see can reionize the universe. So we are close. So what's the answer? Most likely, well, we need to always worry about this. It's called field-to-field variation. These are simulations on large boxes. One is centered on a cluster of galaxies, one is centered on nothing. And the red is neutral, and the dark is ionized. If by misfortune your survey is along this direction, you would see mostly neutral material. If it's in this direction, you will see mostly ionized material. So there can be large variations in the universe about, depending on where you look. So you must be sure that you are, accounting for this properly. But assuming we do, we think that small galaxies and part of the galaxies we see actually reionize the universe. So what happens to the first stars? The first stars cannot contribute too much to the process, but they will contribute a bit. The interesting thing is that some of these stars, depending on their mass, will form supernovae that are incredibly bright, so bright that we could see them anywhere in the universe. So this is very exciting because it means that if you know where to look, or you are lucky, because they are rare, you will see a supernova. You will see essentially the death of a star that was one of the first stars forming in the universe. And that's, that's about as much as you can ask. This is the most distant galaxies that we have observed so far. It's a redshift 10 object. And it is this pushes the envelope of what the Hubble Space Telescope can do. And that's, it would be invisible in the plot I showed earlier, but, it's probably there. So the tentative conclusion is that reionization is dominated by faint and probably metal poor, very low metal content, but non-zero galaxies at redshift 6 and higher. And that the bright galaxies and the quasars, the active galactic nuclei, the accreting black holes, contribute but are not a dominant source. So what can the James Webb Space Telescope do in this contest? This is the easy part, because the James Webb was designed to be a workhorse in this area of science. First light and reionization initially are the T-shirt that were made by the project were saying the first light machine. So we should do this problem well, and we do. Webb is a large telescope. If this is the primary mirror of Hubble, this is the primary mirror of James Webb. It's an international collaboration, 6.5 meter diameter, deployable, cryogenic. The mirror will be at about 40 degrees Kelvin, and it will be launched by a European rocket, an Ariane 5 from French Guiana, into L2, which is a Lagrangian non-stable equilibrium point about 1 million miles from the Earth. If you remember your dynamic, your L4 and L5 are Lagrangian stable equilibrium points. L1, 2, and 3 are unstable. They are saddle points, stable in one direction, unstable in the other. We place the telescope there. That means we need to spend a little bit of fuel to keep it there. Not a lot, because it's an equilibrium point, but a little bit to make sure that it doesn't drift off. It has 4 instruments, cameras and spectrographs in the infrared, and work is going very well. I'll take questions on that. Even though it's optimized in the infrared, it has excellent imaging quality, even in the visible. In the infrared, of course, this is the Hubble ultraviolet field in the infrared, and this is a simulated images of what JWST can do. I can tell you how it was produced, but it is better than Hubble at these wavelengths, and of course much more sensitive. So in terms of the first galaxies, it was designed to see them. It was designed to go to essentially be able to repeat an ultra-deep field survey, but at higher redshift, so to have that margin of extra sensitivity. So it's possible that by the time we launch JWST in 2018, the problem of reionization will be understood thanks to the Hubble, the Planck, the European experiment, and ground-based telescopes. One thing that will be hard to do is to measure the metallicity of galaxies, because that tells us how much energy they put out and how much is the escape fraction. And these probably require the James Webb or the 30-meter ground-based telescopes. But in a way, it's like a detail. But if the whole problem is still an open question, JWST has all the capabilities to completely kill the horse. For the first light objects is a bit tougher. The first light stars are extremely rare. We can see them as supernovae. A single star, it's too faint to be seen before it dies. If we are lucky or if they exist, we could see them as lensed objects with gravitational lensing. We can study the first galaxies, and these are most likely, based on the theoretical bias today, not zero metallicity objects, but low metallicity galaxies that have been pre-enriched by these first stars. And of course, it's important to continue studies to understand what happens. So my conclusions are, and I have no idea whether it was fast, slow, or about right. That we may have observed the end of the reionization process, and we have evidence that it's an extended process. The studies with Hubble have pushed our knowledge to redshift 8 and maybe 10. I'm an author of that paper claiming that object at redshift 10, and I would give it a 50% chance, maybe. So. After we stop recording, I can even tell you why we published that paper, but not before. We have reached the time of rapid change in the luminosity density of galaxies. And so it's possible that with Hubble, we won't be able to do much more than what has been done. Once you spend 2,000 hours with Hubble, it's hard to do a lot more. There are only so many hours in a year. JWST will do major contributions to this area of science, and with some luck, it will be able to see the supernovae from population 3 stars and get sufficient data to characterize them as the supernovae of a star that had 0 metals when it was born. And that's it. Thank you.
Thank you very much. We have some time for questions. If you have questions, please stand up and raise your question. Speak loudly because the auditorium has good acoustics. Yeah.
There are some other possibilities for what could cause some of this. The dumb one is that maybe it's ice. But the interesting thing about ice is that it's sticky. And so you have something that doesn't necessarily bounce when they collide, but sticks together.
Yeah, but
we have comets now, but we probably didn't then. But the more interesting possibility is magnetic fields. How do magnetic fields work with clustering?
Yeah, we in terms of ice, I'm skeptical because we're coming from a hot Big Bang. The temperatures were very high, plus there is no oxygen around or no metals, so there isn't much to work with to make ice. The magnetic field is a little bit more tricky, and that's why I was pretty careful to talk about the first stars, because as soon as you go into the second star, life gets much more complicated. Because a first star has no neighbors, has no angular momentum, because nobody was there to give it to her. Once you start having another star, that star could acquire angular momentum, could develop torques, could entrain magnetic fields, or have a dynamo. I mean, things get more complicated. So I'm not sure that the first stars are much more complicated than this. Well, everything is more complicated than this, but anyway, that magnetic fields are going to be dramatically important for the first stars, but once you go into the second generation of stars, yes, that is already as complicated as star formation. And star formation in our galaxy is not yet a well understood process, just because of factors like magnetic field.
Hubble had a very disastrous manufacturing defect, which was correctable, I guess.
Yes.
What are we doing now that we're talking about a mirror that's many times larger to make sure that we get it right this time?
Many answers. I could answer cynically saying that people don't make the same mistake twice. We'll probably screw up something else, but not the mirror. So our mirror is actually deformable. It has a lot of actuators. The Hubble mirror was semi-rigid, had very few actuators, and the spherical aberration was outside the range that the actuators could correct. The mirror of James Webb has more than 100 actuators. And it's very thin. It has a lot of capabilities in deforming itself. So a small amount of spherical aberration would be correctable. Of course, people know about the history of Hubble. They have looked at everything that happened, both the regular story and the classified story of some additional tests that were done and ignored. So, people have made sure that they understand 100% what happened on Hubble. And so I'm pretty confident that we will not have that problem. But there are a lot of more problems that one could have, of course.
Until one or two of the actuators don't work.
Well, we can work also with some failed actuators.
What about the birth of these solo POP3 stars? I've been taught to believe that a star fights off, gravity makes it collapse, but the heating can stop that, and it will not form unless there's supernovae to squeeze it some more.
Yeah,
What's going on with these solo stars?
So there are a number of comments there. One is that these objects would be pretty inefficient. You start from 100,000 solar masses of gas, and you form say, it's less than that, but even if it was 1,000 solar masses star, you have only used 1% of all the gas that you had available. And that's because of the type of inefficiencies that are involved. In technical terms, one of the views is that this star's growth is essentially stalled by the Eddington limit. When the heat of accretion generates sufficient energy that it balances gravity, then the star stops growing. And these stars, even when they ignite, their nuclear reactions essentially emit at the Eddington limit. So I think the one thing that is not well known is whether you really form one or a small number. In simple arguments like the one I made, it's one, unless the mass of the initial halo is large enough that it would fragment before collapsing, and then you would form a small cluster. Of course, this requires that you have exactly zero angular momentum, exactly zero rotation. Now, it's true that this is the first object and there is nobody else around, but zero is a pretty small number. If you had a very small amount of angular momentum, at some point during the collapse, you might start flattening and forming maybe a disk, and then there the chances of fragmenting go up, and then you would form maybe a small cluster of stars instead of one. For many of these arguments, it doesn't matter, because the amount of energy per unit in mass for this type of stars, it's pretty independent of mass. Once you are, say, about 80 solar masses, whether it's 1/400 solar masses stars or 580 solar masses stars, it's the same. But it could affect things.
Those of us that are not in the know, where is the funding for this in its developmental process? The last time I heard, Congress canceled the whole program.
Well, that is not strictly true. The House, in their first reading of the appropriation last year, had zeroed out the budget. People tell me, I'm not in the know at that level, that this was more of a flag raised of unhappiness by that committee over how NASA had managed this project. But anyway, that's what happened. It was, that's a public matter of public record. It was $0 for James Webb. The Senate passed a bill that had full funding for the project, and then they went in conference and they agreed on the Senate version with full funding. So for the year that we are in, it's fully funded. And in the president's budget that was released in mid-February, it's also fully funded at the level that would enable a 2018 launch date. The project went through what we call a rebaseline, which identified the true cost of the mission now. And if at any time the budget is lower than that from the rebaseline, we wouldn't be able to maintain the launch date. So it would mean that either you cancel it or it's going to cost more and launch later, because the two things go with one another. In this type of projects, if you delay, the cost goes up. So the situation today is good. Of course, Congress hasn't enacted a budget for the next fiscal year, for 2013, so nobody knows what's going to happen. But at least the budget in 12 is good, and the president's budget in 13 is good. And by the way, that rebase line was approved both by Congress and by the executive branch. But of course, things could happen.
There's a law, I can't think of the name of it yet right now, but it's the fact that two particles cannot occupy the same energy level.
Yes.
What is it? I can't think of it.
Exclusion principle.
What?
Exclusion principle.
Yeah, okay. In any of the galactic formation, black holes and everything else, is that law violated to go beyond?
No, the densities of these objects are so low that you don't get anywhere near the type of the phase-space volumes at which those laws take place apply to orders of magnitude different from these densities.
Okay, what about black holes?
Well, there, in certain regimes, you're getting closer, and that's why you talk about black holes don't emit radiation classically, but you can have emission of radiation from black holes. The so-called Hawking radiation is a quantum effect. And the one you were talking about is a quantum effect. So that type of quantum effects can become relevant for black holes. But, the black holes are not directly connected to most of what I said. And the black holes that I was referring to, the one in active galactic nuclei, are very massive black holes, like 10 to the 8 solar masses. And those are a very little effect from quantum physics. If you had a black hole as big as as a mountain or an aircraft carrier, then quantum effects would be dramatic, and I would advise you to run away very fast.
Density of these first stars is very low. When they form supernova, is that a supernova behaving the way we expect one to? You see, near my object?
The density is not very low when once they are formed. Okay, they form from low density material. But first of all, the material they form from is more dense than stars in our galaxy, because remember, the average density of the universe goes like 1 plus z cubed. So if you are at redshift 30, everything is 27,000 times denser than material today. And so the star, in order to ignite nuclear reactions, has to get a core that has the right density and temperature. So they in their cores are very dense, and their overall density is decent. It's not too low. I missed the end of the. Yeah, the supernova. The way they go supernova is very picturesque, because these supernovae are called pair instability supernovae. These stars, I mentioned before that they were Eddington limited. This is the jargon for saying that something has the pressure that balances gravity provided by radiation. It's not the gas molecules eating each other, but it's the pressure of the radiation getting out. So if the thing gets warm enough, some of those photons are going to create electron-positron pairs. And that subtracts a lot of energy because we are actually creating a little amount of mass from energy. That subtracts a lot of energy from the radiation that is sustaining the star, and so the star misses its pressure and collapses. Now, what happens then depends a bit on the mass and exactly what happens. But in some cases, the collapse is such that it gets warmer, produces more electron-positron pairs, loses more radiation, collapses more, and bye-bye baby, you form a black hole. In other cases, you bounce, and you get what we call pair instabilities. The star is like, bounces up and down, and in some cases, the bounce is so strong that the object goes supernova. So it's a pretty complicated thing. And of course, you have recombination of those electron-positron pairs and so on. So it's these supernovae are driven by, they are in this very odd regime that we are not used to, of a star so hot that in its atmosphere it can produce positron-electron pairs.
Yes, okay, that's population 3 stars.
Yes.
What are the population 1 and population 2 stars?
We astronomers are here to help making things as obscure as possible. So the first stars are called population 3. The ones that form next are called population 2, and the one that forms now are population 1. So most of our galaxy is based by 1 and a little bit of 2. So say the disk is 1, the globular clusters are 2.
How is it there are so many binary stars in the universe? The second question is, what in your view that you don't understand bothers you the most?
If this wasn't recorded, I would say the US budget process. But anyway, but aside from that, the binaries are, because when you form stars I'm not an expert in star formation, but when you form stars in the nearby universe, you have a lot of things around, you have a lot of angular momentum, and so things, as you collapse a cloud that is rotating, this cloud will tend to form a disk, and then it's a natural thing to fragment into pieces. It's more convenient to form two blobs orbiting each other rather than dissipating that angular momentum and form a single object. So I think that's part of it. And I think there is growing evidence that binarity, the fraction of stars that are binary, gets higher as you increase the mass of the stars, so that the most massive stars are mostly binaries and the little ones are often non-binaries. In terms of what I don't know, the escape fraction that I had a view graph on bothers me a lot, because where you can measure it most easily is irrelevant, and where you would like to measure it, it's impossible. So it's a very, very, very tricky problem. The reason I'm saying this is that where you could do the measurement clearly is at very high redshift, but there you have so many neutral hydrogen clouds along the line of sides that are clouding the issue. We know with their absorption, individual absorption, they mess things up, so it's hard to measure what's the ionizing radiation coming out. And if you go instead in the nearby universe, you can do in principle the measurement more cleanly, but our nearby universe doesn't give you any indication that the properties are representative of the galaxies at those times. You have a lot of metals, you have dust, you have all kinds of things. So that is I think, a tricky problem.
Yes.
What can the Webb tell us about the expansion of the universe that we don't already know?
I wish I... So, that is a little bit tricky to answer. But, Webb can do some of the things that Hubble does and will do better. So, as you know, Hubble played a major role confirming that the universe is accelerating, the expansion is accelerating, and we can strengthen the distance scale by measuring more distance standard candles. We can, one of the tricks is that if you know the Hubble constant to exquisite precision, you can actually combine with cosmic microwave background experiments. You can actually provide an independent constraint on dark energy. And that's what Adam Rees, that is at the Institute, is working on. And with James Webb, we may be able to measure, the precision that he's getting now in a published accepted paper is 3%, which is amazing if you think that not long ago there were two groups of astronomers hating each other for, and having answers that were different by a factor of 2. So going from a factor of 2 to 3% is pretty amazing. And with Webb, maybe with Hubble it will improve further, and with Webb we may even go to below 1%. And that makes Hubble combined to Planck, Webb combined to Planck, and Hubble too, a dark energy experiment. So there you have a lot. The other thing that Webb can do is to remove any additional doubts that there may be about the systematics of supernovae by going beyond, redshift 3, making sure that they behave as we think they behave, and so on. And of course, there is always the component of, great observatories have major capabilities once you calibrate them and understand them well. So there will be, Hubble has made pretty amazing discoveries that were not planned. And there will be a few more like that in the coming few months. So follow the news. And I'm sure that Webb will be able to also have surprises because it has that type of capabilities.
Do you expect that Webb will be able to discover WIMPs and or dark energy?
I don't think so. I mean, it has the capability to constrain dark energy as an astronomical mission would, maybe by studying lensing, gravitational lensing. For weak lensing, the field of view of Webb is pretty limited. So, it can go maybe a little bit beyond what Hubble can do, but it's non-trivial. So I don't expect, as I was saying, you can always be surprised, but in that specific field, I wouldn't expect major surprises. The only area where there could be a surprise is that, if you recall, alternative gravity theories were put to rest recently by the so-called bullet cluster, where you have two clusters of galaxies coming through each other. All the gas that represents most of the mass we can see shocks and remains in the center. The galaxies go through each other, and by reconstructing through weak gravitational lensing the mass distribution, you find that the mass is with the galaxies, not with the gas. But the galaxy mass alone doesn't do it, so you need dark matter associated to the galaxies to explain this system. And that is very hard to explain with alternative gravities. So it's a strong proof for dark matter. Unfortunately, there is another cluster that doesn't work as well, that came out later. And it looks like it's more complicated. So maybe it's just the modeling that needs to be refined. But if with Hubble or Webb that has similar and enhanced capabilities, you were to find cases where lensing points to properties of dark matter that are odd, then it could be a red flag for something strange happening. But it's somewhat unexpected.
Would you like to explain what a WIMP is, since the audience may not know what the WIMP is in astronomy, not in there?
Yeah, WIMP wasn't an insult. Is a weakly interacting massive particle. So dark matter, we know, doesn't interact electromagnetically because we would measure it in our everyday life. And we know that they don't interact strong, which is the strong nuclear force, because we would see it in the laboratory. So we postulate that they interact with the rest of the universe and with each other through the gravitational force and the weak force, which is weaker than the strong force.
Any other questions? Anyway, the speaker will be around during the social hour, so if you have any more questions, he'll be around to answer them. But join me thanking the speaker for...
Thank you.
In appreciation of your lecture, we have a plaque here for you.
Thank you.
It's the announcement with your picture and signed by the General Committee.
Thank you.
Anyway, thank you very much.
Aside from the picture, thank you.
Well, everything is great, the picture included as well. Thank you.